Hello, everybody. Happy New Year and happy Monday. My name is Teresa Barnes. I'm the director of DuraMAT, and I want to thank you for attending our January webinar. As many of you know, we hold these monthly on a variety of different topics, and our goal is to provide some information about work we do in DuraMAT, like this project, and other topics that inform and influence DuraMAT work. If you're interested in finding out more about DuraMAT, our research portfolio, or our researchers, or our projects, please visit our website at www.duramat.org. Our presenter today is Peter Hacke from NREL, who will be presenting highlights from a project he's been working on looking at the combined accelerated stress testing of bifacial modules, which is a topic of very keen interest to most of you. Peter's been at NREL for 13 years working on accelerated testing of PV modules, and in DuraMAT, most people know him for his work in originating and developing the combined accelerated stress testing technique. And he has recently returned from a 6-month sabbatical at EPFL. So we're also very excited to welcome Peter back to NREL full time. With that, take it away.
Thanks for the introduction, Teresa. I'm going to share the screen here. And go to presentation mode. All right, so my screen should be visible.
Yep, you look good, Peter.
So this talk is evaluation of bifacial modules and PV technologies with combined accelerated stress testing. This particular set of modules came out of a project with Arizona State University. And it's also a collaboration with DTU Photonic and DuPont. So why bifacial modules? Well, they're taking an increased market share, and you have, the monofacial modules slowly losing market share. You actually have a segment of monofacial modules using bifacial cells, and but the bifacial modules is moving from about 30% up to 60%, over the next decade or so. And these bifacial modules with light incoming on the back need something transparent. So that motivates the question, what are we using on the back? Why? What are the concerns? And what can we say about it with combined accelerated stress testing? And that's what I'd like to present essentially today. As we get started in this, we have we had some a priori reliability concerns for bifacial modules based on, some extent of glass modules, glass backsheet modules we've seen out in the field over the last 30 years. And here we listed what we could think of if you have a glass rear, or I used the words substrate. There could be delamination due to a constrained outgassing, based on perhaps incompletely polymerized ethylene vinyl acetate. You could have a PID on the back because glass transfers ions leading to PID. You could have delamination due to adhesion loss. And you could have stress on cells and metallization. Conversely, with a polymeric backsheet, there might be concerns about discoloration, embrittlement and cracking, and there might be also stress on cells and metallization. So these are things that we could, maybe worry about. Maybe there's others, preconceptions other people might have about the pros and cons of what we use on the rear. But these are some, and these motivated our experiments just to some extent, and we'd like to show you what we got with respect to these hypotheses we're testing. So this is the slide is an introduction to combined accelerated stress testing. It's the kind of tests we use to evaluate the modules, glass backsheet modules. The idea is to maximize the representation of what goes on in the natural environment. There's the axis of the sample. And the idea is if you really want to know what's going to happen to the shipping module, we've got to test as close as possible to something resembling the shipping module. Of course, testing the materials, the coupons, the mini modules, and the module itself, they each have their place in the development of a product. But ultimately, we want to examine something that represents what's going to ship to have the increased confidence. In this work, since here at NREL we're R&D, we're working on the mini module level. Then there's the stress factors. Temperature, humidity, light, system voltage bias, mechanical stress. We'd like to, maximize all those factors that you see in the natural environment in a stress test. And we'd like to also put them in combinations that you would see in the real world. So, we could do steady state temperature, like a temperature test, but in order to truly understand what's going to happen, we need to somewhat mimic the diurnal and seasonal cycles that a module is going to see. So to meet this need, the combined accelerated stress testing chamber that we're working with now looks like this. We apply the factors of heat, light, humidity, mechanical pressure, system voltage, and the levels we apply again, and the combinations are per maximum that are seen in nature. There's in situ metrology in the tool to help understand what's going on, such as IV and electroluminescence. The chamber, an image is shown here, and something to point out is that as it deals with bifacial modules, is we have aluminum reflecting troughs here, which send about 7 to 8% of the illumination in the UV range, well, full spectrum, but we're mostly concerned about UV with respect to reliability and durability. Reflecting, these aluminum troughs reflect light to the backside of the module. In other work, we've examined the acceleration factors of some particular degradation modes and mechanisms. And for items such as the outer layer polymeric and the inner layer PET, electrochemical degradation and thermomechanical fatigue, the acceleration factors are in this range here. Some things to point out is like PET, the acceleration factors about in the 400 range, but that's associated with the high activation energy of the degradation of PET in temperature and humidity, leading to a great deal of acceleration. So to keep that in perspective, though, for example, an 85 degrees C, 85% relative humidity test, such as IEC 61215, would lead to an acceleration factor of about 5,000, or just like 2 days in the chamber is roughly 20 years in the field. It's on that order. So even though this is high, this is somewhat a little bit more reasonable than what you would get at an 85 degrees C, 85% relative humidity test. The cast cycle and its climate sequences are shown here. So this represents across the horizontal here, the climates, and in each climate, there's a sequence. We have a dead of winter sequence, which is essentially a cold storage test, but we add dynamic mechanical loading and static loading to the extent shown here. This is the number of cycles and the duration of each pressure. There's a spring cycle, and this is essentially to replicate freeze-thaw. The maximum temperature of the air in the chamber is 15 degrees C, and the maximum temperature of the module is 35 degrees here. So it's relatively modest levels of that we see in terms of temperature. And there's water spray again to replicate to achieve the freeze-thaw cycles that you might see. Then there's a tropical, and this is the first one we applied, and it's from ASTM D7869. When I say first we applied, we started combined accelerated stress testing with this particular cycle, but it's evolved to include all four that we're looking at here. It's the longest, and it involves a damp heat sequence, a light soak sequence, a quick low temperature sequence, and then basically a set of sun showers were alternating between sunlight and water spray. And this was developed for the paint and coatings industry to prevent the kind of peeling you see on some paints on cars. So the auto industry was seeing that problem, and they needed a better accelerated stress test to deal with that and prevent it. And this, replicates a lot of the philosophy of what we do in combined accelerated stress testing, where we're looking at the temperatures and of what the product gets to in the natural environment, and replicating the cycles of the natural environment into a test. And then finally, there's a high desert sequence, which is it's in the dry. We maintain the relative humidity very low, and we're cycling with light between -20 degrees C and 55 degrees C air temperature, and the modules get up to 90 degrees C. And that's true in these two sequences here. The module sees a maximum of 90 degrees C, and that's somewhat, that replicates the highest temperatures that modules get to on a close mount roof in, say, Arizona, or a building integrated product where the back doesn't have free airflow. So that's the philosophy of the combined accelerated stress testing, and these are the cycles that we applied in the tests here. So I'm going to go through a few experiments and the results, and this is the first set of results, or first category of results I'd like to walk you through. And the experiment involved monofacial PERC cells with two encapsulants and 3 substrates as shown here. The encapsulant was POE and EVA, polyolefin, elastomer, and ethylene vinyl acetate. And each of these had 3 different substrates: transparent PVF, glass, and a white PVF, polyvinyl fluoride that is. And the samples are shown here. They went through differing lengths of combined accelerated stress testing as shown in the rightmost column. So the interesting results here are in the electroluminescence, where we're looking at the initial electroluminescence and the final electroluminescence of all those samples. One of the things we notice is that the samples with the glass substrate, whether it be polyolefin or EVA, seem to show the most grid finger breaks when examined after the end of testing. And what we're looking at here is a quantification of the numbers of breaks that are observed at the beginning and at the end. And we can see, as highlighted in the red circles here, is again, the ones with the glass substrate seem to lead to the most grid finger breaking. Here's a close-up, and what we're seeing is that it's not 100%, but there's some relationship between the rear bond pads and the grid finger breaks. The fundamental origin of these kind of grid finger breaks, or the weaknesses, might be potential over temperature in the soldering, which leads to embrittlement. But that was the case through all the different samples in the experiment. It's really seems to be, based on the data, the glass substrate was what precipitated finally the increased grid finger breakage. That said, there was negligible fill factor and power loss in all of these samples. Despite the grid finger breakage, the extent of power loss was still fairly minimal. So it's something that could develop potentially further over time to lead to power loss, but to the extent we tested, the power loss was despite these important electroluminescent signatures, was rather minimal. It's worth reviewing the literature to explain what might be happening in the grid finger breaks a bit. Our very own DuraMAT, that's let's say this DuraMAT project is carried out by Mariana Bertoni's group. Well, it's her project, this DuraMAT is, but they found X-ray topography, thin film plate theory, and finite element analysis showing a great deal of stress at the in glass modules with the tab ribbons, especially at the ends and around the edges of the cell. And they saw, you know, in terms of the top 0.1% of the first principal stress values, the very highest in the glass modules compared to, say, the glass backsheet modules. So there's a relationship between these two DuraMAT projects, whereas they did the modeling and some testing, we did the stress testing, and you know, we can see the commonalities, which I thought was fairly interesting. Then also finite element analysis of stress strain in copper interconnects in temperature cycling. They found the highest mechanical loads appear in the glass assembly, and that would be the dotted lines here. And but more importantly, this area in the glass corresponding to the glass modules in the space of stress and strain was the greatest. So there's the maximum accumulated plastic strain of some elements in the glass reaches double that of glass backsheet assembly, as you compare the two different areas of the glass backsheet and the glass modules. So there's quite a bit of stress formed apparently in glass modules that manifest at the edges of the ribbons, and that could be contributing to the failure. Also, we have to consider that glass modules, if there's any of what we call pinching here, leads to also some additional stress, which could further exacerbate things like what we see, grid finger breakage at the edges of a cell, or I should say the edges of the cells at the edges of the modules. So in summary of this little section, the glass modules show higher stresses in silicon and interconnects than in glass backsheet modules, and we found 3 times the grid finger breaks in the glass modules. Okay, I'm going to shift gears to move to our second experiment, and this involved bifacial PERC cells with 2 encapsulants and 2 substrates. So we had 4 cell mini modules again, and the details of the experimental matrix are shown here. We had encapsulants of EVA and POE, and we also had transparent polyvinyl fluoride rears and glass rears or substrates. And all of these went through 3 cycles of combined accelerated stress testing. We also did some ex situ experiments, and that I'll walk you through. And here we're looking at the pictures of the modules. Okay, so in order to fully explain the results, I need to give a little primer on one of the degradation modes we found, and that's potential induced degradation polarization. And this can occur on the rear of bifacial PERC. So it happens on the rear of PERC, and the reason for that is because the rear of a PERC cell, a bifacial PERC cell, it's undoped, and it's very sensitive to the dielectric charge state. So what we're looking at here at the right is a bifacial PERC cell with the rear with the passivating coatings of aluminum oxide and silicon nitride. And what happens is that any change in charge here, for example, if we see positive charge developing in the rear dielectric, that would attract minority carrier electrons from the base to it, leading to further recombination and annihilation of charge, leading to degradation of power performance and short circuit current and open circuit voltage. And yeah, so that's what's going on there. It occurs most in EVA glassback modules. That's the encapsulant would be EVA, and that's because historically, typically, not always, but generally speaking, the conductivity of ethylene vinyl acetate is higher, leading to charge transfer and leakage current through the rear. It occurs in negative system voltage. It builds up positive charge in the dielectric, as I went through just a minute ago. It's generally correlated to higher leakage current, whereby leakage current goes through the glass and encapsulant. And the degradation is greater under low light or in the dark. And on the other hand, a recovery occurs under light soak. And the whole reason for this light sensitivity is because silicon nitride is photoconductive, and that photoconductivity can lead to annihilation of charge, reducing the amount of buildup and reducing the amount of PID polarization. And finally, recovery under opposite system voltage polarity occurs. So here we have degradation with the cell under negative bias, but if we were to, that negative bias would attract the positive charge to the dielectric here, but leading to the PID polarization. But if we were to reverse the bias on the cell, we drive away that positive charge back out towards the glass, and the PID polarization we saw would recover. So that's kind of a primer on PID polarization to explain what it is we see in the next slides. So what I've done here is first put a scatter plot of all the data, but I'm going to drill into the data of interest in just a second. But let me explain what I've done to try to explain what I've done to try to clarify the picture. Excuse me while I get some water here. So what I've done is color code the different climate sequences and that are labeled on the bottom. So the dead of winter and spring are in green, and the test we take after it is shown as spring. The tropical sequence is split up into two different parts because it's rather long, and that's highlighted in blue. And the high desert is highlighted in orange. We also did some ex situ light soak tests, putting the modules out under sun to see what happens for some additional diagnostics, and that's in white. Okay, so I'd like to focus the attention on the glass EVA front measurements and the glass EVA back measurements as shown here. So I've highlighted those on the table here and dimmed all the other data to help us see what it is we're talking about. So what we notice here is that these particular modules, which degrade a good deal, and here we're looking at flash tests from the rear, and here we're looking in the solid line as flash tests from the front after the given stress sequences, we're seeing that the modules with glass back and EVA encapsulant shows the most significant loss in ISE and VOC from the rear in bifacial perk. So more or less consistent with, well, I should say consistent with, PID polarization. This kind of degradation was associated with the glass EVA module construction. It did occur with negative 1,200 volt system voltage bias applied to the cells. These particular modules that are shown here with the glass EVA in purple did exhibit the highest leakage current. And the degradation was under low light conditions, that's to say in spring. Especially here in the spring is where it degraded the most. And again, here in green, it degraded the most. And there was recovery with elevated irradiation. So for example, when we take the modules out for diagnostics and put it under sun, we saw recovery. But also here, when we went from the spring, which has low light, to the tropical, which is higher temperature and full sun irradiance, we actually also see recovery. So this, and also this final point here recovery under opposite polarity. So just to more or less put a nail in the coffin with respect to, I should put it more optimistically, just to kind of confirm our hypothesis that it is PID, we actually took, at the end of the test, we took the module out and biased it under the opposite polarity, positive 1000 volts. And this particular purple module, module with purple points, quite significantly recovered with application of 1000 volts. So, with all these bullets here checked off, we make the conclusion that the glass back with EVA encapsulant module could show could be showing potential induced degradation in the polarization mode. So this has some implication for the standards. The 61215 2021 series of the PV module design qualification and type approval involves a PID test, which is 85 degrees C, 85% relative humidity, 96 hours with system voltage in the dark, some modules in positive voltage, some modules in negative voltage, to see their PID susceptibility. Then a final stabilization is called for, and that calls for specifically 2 kilowatt hours per meter squared of UV irradiation on the rear to eliminate polarization, so-called artifacts. And then there's a flash test. But the problem is when we do combined accelerated stress testing, we find PID polarization, and so this polarization may not be an artifact. It looks to me, based on the conditions we applied that are very realistic in the real world, that this PID polarization could happen on the rear of bifacial PERC modules in real life. So just to look at the data again, to hit that point and make it go home, is we saw an important amount of degradation in this spring cycle here, and then recovery under light soak to some extent, and again degradation under spring and recovery under higher temperature and higher light. So again, this module type would be susceptible to PID in the field based on our results in the spring conditions. And the 61215 2021 has a 2 kilowatt hours per meter squared UV rear light soak that may hide PID polarization in PERC. So I would say that there's some problems with the standard in evaluating, and basically some problem with the standard in the sense that it refers to polarization as a artifact, but in fact, it could happen in field conditions. So I'm going to move on to the second of the two degradation modes we saw in the bifacial PERC modules through combined accelerated stress testing. And in order to do that, I'd like to give a primer or a reminder about what goes on in light-induced degradation, the boron-oxygen complex type. So Herguth at University of Constance was kind of pioneer in understanding all of this. So he had this little simple diagram here. It's a generalization, but nevertheless, it kind of is useful to explain what's going on. So if a brand new cell, if no special treatment has been done, is in this state A. It's called annealed or inactive. And what happens is if you just put it out under some modest temperature and modest light, it would degrade by light-induced degradation. On the other hand, if you take the cell and you apply under high temperature and light a sequence here, or instead of light, one could use forward bias electrical current to get the carriers where they need to go to lead to this so-called regeneration, you get to the C state. Now, the way it works in life these days is that module makers know this, and they if at least, you know, best practice, I would say, is companies, module makers, cell makers, module makers will sell their modules with cells in the C state. So they'll do some kind of process with bias and temperature at the end to get their cells and modules stable so that you won't see LID. Now the issue is that this so-called regenerated inactive state is, you know, it's fairly stable, but there are already known ways to destabilize it, and that's high temperature in the dark. So the models aren't exactly clear, or there's a little bit of discussion among experts about exactly how things work. But basically, if you put it at high temperature and with no light, these you can get out of this C state and then lose power. So what we did to understand, you know, how the cells and modules we were working with behaved, we checked them out and we ran them through this little sequence that I'm showing here. So we took one of these new, you know, nothing to do with CAS now, but another replica of modules we had that had polyolefin encapsulant and glass on the rear, and we put it under the sun first, and then in dark heat, and then under sun again, and that's graphically shown here. So first, the module we assume is shipped in the C state, and then we expose it to a light soak outside for a couple days, almost a week, and we see that there's no change in power. So one would assume that, you know, this is kind of a state C, regenerated inactive state, or, you know, it just doesn't exhibit light-induced degradation. Then we did a destabilization sequence to understand, well, if it adhered to this model, whereas if we destabilized it, we would lose power. And sure enough, at 150 degrees C, 66 hours destabilization sequence, we see a little bit of degradation. And then when we put it under light again, in this case, less than what we did the first time, 30 kilowatt hours per meter squared as opposed to 40, we see an important amount of degradation. So what this is telling us is that the samples types that we're using fit perfectly to this understanding of this particular model here out of University of Konstanz. These modules were shipped to us in the state C, regenerated inactive state. So now we're going to look at our data again, and I'm going to highlight the modules of interest here. The focus will be on the modules with polyvinyl fluoride or glass substrates and polyolefin encapsulants. And what we see is periods of before getting to this, periods of degradation and then recovery again, and then it's repeatable periods of degradation and then recovery. So what's going on here with some view towards this model is that we're applying during this tropical and high desert sequences light and up to 1.9 suns and 90 degrees C, the modules reaching 90 degrees C temperature. And during the course of this period here, we should be in this state C, regenerated inactive. We are applying light and according to the models, and these would require some kind of, in order to get degradation, the lights would have to be off. But here the lights are on, and but the issue is that when we went to this spring sequence here, we saw a little bit of degradation, especially when measured from the rear, up to about 5% degradation as in ISC, for example, roughly speaking. So we kind of scratching our heads about this, and for additional diagnostics, we took it and put it under natural sunlight, and we saw yet further degradation. So this is a little bit unusual here because none of this model doesn't really have a situation where you get destabilization with temperature and light. All of these models to get degeneration or to move from the state C to state A or state C to state B involve darkness. But we had the lights on, and yet we saw some kind of degradation. And then what we also saw when we took it out of the chamber or in spring sequence is shown here. But we continued on with the tests, and what we saw is when we moved back to the high temperature 90 and high light areas here, we saw regeneration again. The power recovered, and that's kind of consistent with moving from state B to state C, where we're going at high temperature and light. So this part is good, and as expected, but unexpected again for the second cycle when we take it out for a light soak in modest temperatures. Well, basically outdoors, we see an important amount of degradation. And then again, for the second time, when we bring it to high temperature in the tropical, we see recovery, again, consistent with moving from the state B to state C, where we're getting regeneration with temperature and light. So the problem is this degradation, as pointed out by my cursor here and cursor here. The models say that we should be in the state C, and we should remain in the state C even when we have temperature and light. In fact, we're getting degradation. So to understand this a little bit further, we took a new module and light soaked it ex situ, let's say in natural sunlight, and we took these modules at the end of combined accelerated stress testing, that's to say after high desert shown here, and just put them out under light soaking as well, and we see the new module has no degradation, but the modules that were exposed to combined accelerated stress testing do degrade under light soak. So this is a bit strange. So we looked at the literature, and the only literature that we could find that I could find that showed this kind of behavior is out of ISFH in Germany, where they did the stabilization procedure at high temperature and illumination, and then they more or less like us, they put it out under regular, ambient temperatures, modest light, and then they saw a degradation. And the issue was that it was a boron doped P-type, but phosphorus compensated CZ silicon. So it could be that depending on the impurities you have in the module, in the cell, that you might do a regular IEC 61215 light soak, but in real world conditions where, well, I should say like building integrated PV where the module gets to high temperature, we could see some degradation even passing IEC 61215. And this graph here is to illustrate what's going on. IEC 61215 2021 series, the PV module design and qualification type approval, involves an initial stabilization where you're required to put it under 10 kilowatt hours per meter squared, 50 degrees C. But what we found is that higher temperature and longer light exposures, as with combined accelerated stress testing, tropical and high desert, might lead to LID destabilization, which won't be seen in IEC 61215. So, it could potentially, a module type that we tested here does just fine under a regular light soak as shown there, but in combined accelerated stress testing, which replicates kind of worst case conditions you can see in the field, you would in fact get light-induced degradation, and this is missed by IEC 61215. So I'm going to summarize here, and first, what we're looking at is the filled out chart that we looked at in the very first slide, which had the a priori considerations of what we might see in glass versus polymeric backsheets. Well, on the glass substrates, we found no delamination due to constrained outgassing. We did see PID on the back of, when we had a glass module, especially with the ethylene vinyl acetate encapsulant. We did not see delamination due to adhesion loss in any case. We did see stress on metallization in an important way. With the polymeric backsheet, we did not see any discoloration or embrittlement or cracking of the backsheet. In all cases, it was with polyvinyl fluoride backsheets, either clear or white. Of course, we only ran up to 4 rounds of combined accelerated stress testing, which might be like 5 years in the field. So it's not 20 years worth of testing we did, but just to clarify that. We saw no PID on the back when using the polyvinyl fluoride backsheet. We saw no delamination due to adhesion loss. And we did see some mild stress on the cells and metallization, because even if we saw more grid finger breakages on the glass modules, we did see an increase in grid finger breakage as well with use of the polymeric substrate, even though it was 3 times more with the glass substrate. So we additionally found that combined accelerated stress testing spring sequence showed PID polarization. So this was in the glass substrate with ethylene vinyl acetate encapsulant, the type that is susceptible to PID polarization. But in terms of the standards, what we're seeing is that the 2 kilowatt hours per meter squared that IEC 61215 has in it would mask that polarization. And installed modules in the field do not necessarily get 2 kilowatt hours of meter squared of UV dose. So bottom line is that bifacial PERC cells with glass backsheet and ethylene vinyl acetate encapsulant can show PID polarization, and it isn't an artifact. It could happen in real life. Then we found a combined accelerated stress testing destabilized LID regenerated inactive state cells, leading to power loss in the spring cycle and ex situ light soaks. This is also not likely findable in IEC 61215 because that doesn't mandate going to a high temperature or any anything more than 10 kilowatt hours per meter squared of light. So these two items we found, PID polarization and destabilization of LID, could happen in the real world and wouldn't be found in the standards. So that's the end of my talk, and I'd like to thank the support of these projects here.
All right, well, let's take a minute to thank Peter for an absolutely excellent talk. I definitely caught the short version of it in Milan, and I'm happy to hear it in more detail now. We have some questions submitted already to the Q&A tab. Just as a reminder, technical, oh my gosh, it's not working questions go in the chat, and then technical questions about the work go into the Q&A, and we encourage everybody to submit Q&A, and we'll work through them as efficiently as we can, but we do have about 15 minutes for questions. So Peter, the first one is a clarification. Just to clarify what you mean by suns, is that 1,000 watts per meter squared?
Yes.
Okay. And then there was some discussion, I think you're going to notice a theme of questions about the stress.
I'd like to just clarify.
Sure.
We do, for the purpose of our testing, we calibrate on 340 nanometer band.
Mm-hmm.
But at the start of the work, we do a relationship between we make a relationship between the that 340 nanometer band and the full spectrum. So with a light core, the full spectrum is measured with a silicon detector with the light cores on the sample plane.
Okay. So thank you for that. For people who are maybe a little less familiar with accelerated testing, the kind of nuts and bolts of it, one of the really difficult aspects of CAST is getting accurate dosing of light into the chamber at the right spectrum and the right intensity. So Peter and company go to great pains to get that correct. So there's a quick follow-up question on the EL images.
We could always do more. Thank you for your confidence, but there's always more to be done. Yeah.
Well,
please.
you know, if there wasn't, we wouldn't have jobs. So we need, you know. So what did you see in terms of other EL artifacts? I think this is referring to some of the mechanical stress on cells and metallization section, because there's a couple questions on that section. Did you see, Henry asked, what were the other EL artifacts you saw?
Yeah.
And then Dave had a question about slide 5, if it's convenient, just stay on back there.
So here's, what we're looking at after, the electroluminescence, for example, in this set of modules. We didn't, yeah, I mean, you can kind of see some other developments, like maybe some crack formation here. Yeah, and typically, I don't have any slides in this deck to show you, but typically as VOC and ISC degrade, it indicates a loss of lifetime and the electroluminescence gets a little bit dim. But that wasn't really seen in this sample set. It was seen in the second set. That dimming was seen in the with the LID and PID, but I don't have any in this deck to show you.
Okay. So Dave asked a follow-up question on this slide, which is with the glass mini modules and grid finger breaks. Did you see this on both sides or just on the back surface?
So we didn't do cross-sectional metallography on these samples for a deep dive, but what we're looking at here in this particular electroluminescence image is, through the front of the module, although we also looked at the back. But what we're looking at here is rear bond pads. We know they're rear bond pads because when we look at the front of the cell, they try to minimize shadowing, they try to minimize silver, and you don't see any large pads like this on the front of the cell. So we know that these large dark areas correspond to bond pads on the rear of the cell. And we see a strong correlation, for example, in this yellow circle, a strong correlation between these grid finger breaks and the existence of this rear bond pad. So based on that, I would say there's a good but not exclusive correlation between the rear grid fingers and there's an important correlation between what's going on in the rear and the breakage that we see, and that's about the extent to which I can answer the question, because we haven't done cross-sectional metallography.
Okay. So another follow-up on this section of the talk, which is something we discussed in detail at the DuraMAT workshop, which is, why are these observations not observed industry-wide? Like, usually thermal cycling tests show the opposite of glass doing much better on full-size modules than glass backsheet, going up to TC 600, 800, and 1000. What is the different thing that we're seeing here?
Well, I can't really, I mean, we'd have to look at each individual data in order to kind of see exactly what we're saying. But I mean, on a high level, to answer the question is, We're introducing in a given test a number of stress factors that, say, a TC 200 minus 40, 85-degree test does not apply, for example, in that case, mechanical pressure. We also apply mechanical pressure at all temperatures, low temperature, high temperature. For example, we're applying mechanical pressure at low temperature where encapsulants has modulus of elasticity which vary by order of magnitudes compared to room temperature. So these are example differences, and we feel like we need to apply those in combined accelerated stress testing because in real life you might have snow loading when the sample's very cold, like not at 25 degrees C when in a lab. So we feel like we're doing a good job at, well, I should say our work is to do a good job at replicating what happens in the natural environment. I'd also like to point out that, I don't think what we found was out of the ordinary or totally unexpected because, these prior results in the literature, and including those out of DuraMAT, show some consistencies where glass modules have higher principal stresses, especially around the metallization, where there'd be a grid finger breaks. So I don't think what we saw was, I would say, out of common sense.
Well, I mean, I think we're trying to understand. I think the question is intended to understand the differences, as we actually like to see differences between our combined accelerated stress test results and sort of conventional testing, because there's probably something to learn in there. And I think this is a topic that we're going to continue to dive into in DuraMAT. We know in some cases it's related to sample construction, and actually, I think, Peter, you've got that illustrated there on the bottom right. And in other cases, it's related to some physical phenomena we don't understand yet. So I think that gives us an area to continue to study.
Yeah, and I might add that the whole reason, like, I hate to put it this way, but the whole reason we initiated this combined accelerated stress testing was exactly for the premise of the question, and that's we were seeing all kinds of failures in the field, which the IEC 61215 based or extended tests were not finding, such as polyamide failures, PVDF failures, LID, well, not LID, say PID, LETID. So all of these things were more or less, found after the module shipped, and it's only like years later that we got around to develop mode-specific tests for them. And this kind of frustration is what leads to the development of combined accelerated stress testing.
Yeah, I mean, I think we have a lot to learn about what it's telling us, and how that relates to the field, and that's a rich topic for continued research. A quick question: was this a P-type? What's the dopant of the P-type PERC, boron or gallium?
Based simply on the age of the cells and the modules, it's boron. But did we go in with SIMS to measure it? No. Okay. But we, after discussions just based on the time frame and the behavior, looking at, say, a figure, where was it? A figure like this, this is classic boron oxygen light induced degradation.
Yeah.
So we're missing SIMS data. We did not measure that.
Okay, that's a reasonable assumption, though. So it looks like the certain PPERC samples partially recovered to 70% of original power from 35 by running PID reversal in the lab. Did you try running LETID reversal in the lab also on the same samples? They're basically wondering why didn't recovery go to 100%?
The second part of that, yeah, the final part of your question, I'll start with first. Why didn't PID recover to 100%? And that's because this silicon type also exhibited LID. So the even though in that particular sample, let me get to there and show you. So the question is like, where was it? Yeah, here. The question is like, after, you know, we're at this stage and we're kind of trying to recover it, why do we still have an extent of degradation? And the thing is that this particular sample, the purple type, being a sample with EVA encapsulant and glass substrate, was of a type that exhibited, based on its construction, PID polarization. That doesn't mean that it wasn't also susceptible to the other degradation types, such as LID, or even perhaps LETID. We kind of focused on LID as opposed to LETID because since that was mentioned, I'm going to kind of get to that. Like, why not? Why did we consider LID as opposed to LETID? And that's because when we stress test to samples, for example, let me find a better here. So for example, we're coming out of a light soak here, in air, 30 kilowatts hours per meter squared outside on the concrete deck outside the building. And then we go to a high temperature and we see, according to the tropical cast sequence, and we see recovery. So LETID is you know, degradation at high temperature. We saw recovery at high temperature in a very short amount of time. So what we're, you know, whereas LETID is degradation at high temperature, we saw degradation mostly at low temperature, such as the light soak, you know, right, performed here and here. So it's kind of opposite to LETID. But if there's somebody who thinks out there, you know, that this kind of behavior we see, whereby you kind of bring it up to high temperature and high light and see degradation, here you have, sorry, in recovery, this is lifetime, so this is recovery or improvement in performance, and then you just kind of you bring it to room temperature under low light and you see degradation. If this is an LETID signature, well, it's news to me, and I'd be happy to see the paper about it.
Okay. Well, with that, we are at time and we've got to wrap up. I would like to thank Peter for a nice presentation and our audience for great questions. Please join us next month. We'll have a webinar coming up on an app you can use to do your own thermomechanical modeling of module designs from Nick Bosco. And thanks, everybody. We'll talk to you next month, and get your PBRW abstracts in and get signed up before it fills. Bye.
Thanks for joining the talk. Bye-bye.
Thank you.